Okay, we're going to start the final presentation a little bit early. I know this one's going to run long, and I also want you to get out of here early. Sitting through all these lectures is actually quite a bit of effort. So we'll start with performance portable languages. And this came out of series of workshops that the Department of Energy put together when they were first trying to port over to GPUs. And they said, we can only afford to do this once, so we want to have code that is portable when we get to the end of the effort. And so COCOS comes out of Sandia National Laboratories, and Raja is out of Lawrence Livermore National Laboratories. In many ways, they're very similar. So I'm going to talk mostly about COCOS, but it applies much the same for Raja. And then I'm going to talk about C++ standard parallelism. So you can compare the two of those approaches and see which one you think is more interesting for you to perhaps consider using. So DOE started these PPP conferences, which are performance, portability, and productivity. So at SC, they have a workshop on that, and many other conferences, they have a workshop on that topic. And the two most popular are COCOS and Raja. There are others that work along the same lines. There's one called YACL, yet another kernel language. It's very appropriately named. Like we need another one. There's OCCL, OCCL, which is another kernel language, but they're targeted towards specific code domains, like weather. So COCOS is the most popular of all of these, and although it started at Sandia, most of the developers now are outside of Sandia. There's many universities adding to it, and other organizations. Raja is similar. Raja is more modular. So if you know Sandia, they write their software and they put it all in the same very large stack of code. Trilinos, if you've heard that, COCOS was part of Trilinos. So it's a huge software stack and everything gets thrown in there. So it's more of a comprehensive approach. Raja, the Livermore codes all do different things. So they had to adapt them so that it was a modular structure and each code adapts it for the way they want to do it. So there's different philosophies there, but they are very similar. And they're both good choices. I've worked with both teams. They're both really excellent programmers. And they'll both exist for quite a while because the DOE codes basically use these so that they don't have to, for example, when Aurora came online with the Intel GPU, they just changed these packages and the applications didn't have to do anything. So they have really bought into it. The other thing is COCOS has worked hard at putting parts of what they have developed into the C++ standard. The first thing you're going to see is something called MD-span, which is a horrible name. I'm sorry. It's a horrible name because what it is 2D multi-dimensional arrays. And I don't know why MD-span. It doesn't really. And so C++ has finally gotten to the point where Fortran was 40 years ago, where you can do multi-dimensional arrays. But that's a huge step forward because we all had to write our own allocators that would do that. So they are pushing into the C++ standard, and they would like nothing better than all of their work to end up in C++, and Cocos would be doing very little. So with Cocos, you write loops in C++, and you can generate code which will run on a variety of hardware, including serial, OpenMP CPU, OpenMP backend, HIP, CUDA, one API, and so they generate the code for all those devices. And they will generally get as good a performance as you're going to get writing code, because they really understand the hardware. And if you tell them that your code is faster than Cocos, Christian will be running down the hall to find a terminal to try to beat you. So they really are paying a lot of attention to the details that you don't have time to worry about. So Cocos has had a HIP backend for quite a while, and back before there were even data center GPUs. And in 2022, they promoted it to production status. They have things like, if you supplied a certain GFX model, it'll be GFX 942 _ APU, they will actually do single memory for you. So they handle all of that. You don't have to worry about it. So Cocos is Greek for grain, seed, or kernels, which is an appropriate name. It's really heavily based on C++ templating. So what they have done is, by using C++ templating, they can create basically a compiler as a library. It's much easier to distribute a library than a compiler. It takes many years to get a compiler. So this is very effective at extending the language for the GPUs. And I already mentioned MD-SPAN will be in the C++ 23 standard, so should be showing up pretty soon. So in looking at Cocos, one of the things I want to get across here is the basic things you've got to do for a GPU program. And for a GPU programming language, you need execution capability and memory handling. And the MI300A handles a lot of the memory issues, so it becomes a lot easier. But the execution capability is, you have to somehow tell the compiler or your language that you want to move that loop to the GPUs. And we'll talk a little bit about what that means, what the techniques are. The memory handling, we move memory, or we actually want to tell it what memory space to put things in, like the shared memory on the GPU, so that we can get the highest performance even though we're programming at this higher level. So those are the abstractions we want to pay attention to. And so execution spaces, there are basically 3 execution patterns we have in any code. One is a for loop. Second is a reduce, and the third is a scan operation. And OpenMP was missing the scan operation until last year when they added it to the standard. So these are all key. Scans are really important for, especially when you have unstructured grids and you don't know how many of everything you have on the system. A scan will tell you where your starting address is for each thread, for each processor. So it's crucial for parallelism. Execution policies. So we want a portable way to have range policies. And what COCOS does in all of these languages is they split your loop. So in your loop, you have the operations that you want to do on the GPU. And by using functors or lambda operations, they encapsulate that to send it to the GPU. And then the indexes, the range, the things you're going to operate on, has to be called on the host. So you tell it what your loop indices are going to be, 1 to n. That gets done on the host, and the actual code to operate it goes to the GPU. So that's why all of these languages really leverage lambdas or functors to separate those two out. And that's the trick. That's what they're doing. And then we can use team policies to group threads into teams and perhaps use something like the shared memory on the GPU. That's for really low-level optimizations. Memory spaces, one of the things COCOS has done is they allow you to specify the memory layout as layout right or layout left, basically C layout or Fortran layout. You can switch from one on the CPU to the other on the GPU without much effort. And then they have a bunch of memory traits you can access for special operations. So COCOS, there's two ways to use it. You can build an external build and then pass that to your build system, or you can do an inline build. And I think in this one, I'm going to show you the inline build. So you make it a submodule in your source, and you build it at the same time you build your code. And because it's mostly templating, it doesn't take long to build at all. It's very, very fast. So we'll do this inline build, I believe, in this example. So I've got two examples. One is the stream triad, which is 1D. I think I put the shallow water, which is a 2D problem in here for this presentation. Get in the stream triad. So this is a 1D problem. And here are the steps to convert it over to COCOS. We're going to build a separate COCOS package, put it on the system, and then we're going to pass that to our build system. And COCOS uses these different architectures to specify what the back end is. I'm using Vega 90A, but they have newer types for the MI300A that you can use. We also specify the CPU type. We can turn on serial and OpenMP. I think I have to separate, I have to do OpenMP separate from the GPU type. And then when we want to use it, we're going to just point COCOS dir to that package where it's located. So then we have to modify the build. And here's an example of the stream triad. And you can grab this example and go through these steps to convert it over. So this is a CMake-less build system. So we just do find package COCOS required. COCOS has worked really, really hard to make it very CMake friendly. And then you basically just have to change the link libraries. So once you do that, your build system is converted. We haven't touched the code yet. So then what we're going to do is add COCOS views for the memory allocation of arrays. So views is what COCOS terms their memory memory allocations. So we have to include Coco's core header file. And then we have to initialize the Cocos environment and finalize it. And you need the braces, or else when it terminates, it will throw some errors. And then we just replace our array declarations with Cocos views. So these were 3 1D arrays. So we're just call it a view double and give it a size. And then we can rerun again. So this is summarizing what do we need to create to basically make our code Cocos compatible. We just have to add this initialize and finalize in the header file. The memory, we can give it data labels. This will allow the debugger to print out what data you're working with. For 1D, you can either use the square braces or parentheses. And it's because in 1D, it doesn't matter. In 2D, we're going to have to use the parentheses. Cocos does the deallocation automatically. Oh. And one of the parameters that I think you should use is this view allocate without initializing. Otherwise, it's going to initialize it, and that can be slow. That can take some time to initialize the array, although it does avoid errors on uninitialized memory. And you can take an existing array and do what they call an unmanaged view so that you can bring it into the Cocos environment. So then our next step is to add an execution pattern, a parallel 4. I think this is, although it looks a little bit complicated at first, it's basically we're going to add this parallel 4, and then we have the option of using this Cocos Lambda macro to capture the data that's needed for that Lambda function. Now, this can get a little bit complicated to understand, but they've tried to make it as easy as possible. And then you end up, you're going to create that loop, open up the region for that loop, and then at the end of the loop, you're going to finish with this closing brace. And that's all you have to do to convert that 1D array to running in parallel. So this is fairly non-intrusive to convert over from a standard for loop. Okay. So they've worked hard to make it look clean to the programmer. Now we have the option of adding Cocos calls for the timer. You can also use your own timer. Here I'm just showing how you use Cocos to do the timing. And then so our completed version of the stream triad, if it ever comes up, is this is quite readable code. So we've got the views here. So we have the views here. We have the parallel 4 on the initialization. We have the parallel 4 on the loop. And I think to any programmer, they would not find this very difficult to understand. Now, there is one disadvantage that Cocos is somewhat opaque in if you hit a bug, where is it happening? So it takes a little more effort to debug Cocos code. But the plus is this is quite readable code, and it can be run on serial, OpenMP on the CPU, and on various GPUs. Okay. Cocos comes with a very simple set of tools for performance profiling. So you can build those tools and then run the application with those tools. And I'll show an example of the output it has. We've also done a lot of effort with our AMD tools that I'll cover on Thursday to make it work with Cocos. The biggest problem is that their templating makes the subroutines, 5 miles long, and you have to find a way to make them readable. So very simple to get a profiling. So now we've sort of shown for a simple 1D code how you convert it over to Cocos. The Cocos team has very nice tutorials if you want to dig in deeper. But this shows you basically how to get a simple application running with Cocos. I want to step through. I think the 2D I did not include here. I just showed the 1D. The 2D is just a little bit more complicated in that your indexing is two-dimensional and it looks like Fortran syntax. So I, comma, J, like you would have in Fortran. The other thing that the 2D shallow water code goes over is how to do reductions. So keep that in mind. And now let's look at C++ standard parallelism. And this is actually part of the C++ 17 standard, part in 17 and part in 20. And so this is an early implementation of those standards. So the C++ standard has a lot of algorithms built into it. And so there's things like sort, copy, for each, transform, and we can basically take this routine that you see here, the transform function, and it's going to specify again the index set, where we begin, where we end, and then a operation down here, return, that's going to be the body of the loop that we're going to send to the GPU. And we can add this, the sequential would be the serial code, but we can add that part on sequence to say, generate code, which will run on the GPU. And what it will do is take that algorithm and call the corresponding rock thrust routine for it. So it leverages rock thrust very, very heavily. Okay. So there's a blog post on this, and you can look for that blog post. I'm going to summarize it here. But basically, if we provide this one compile flag, it will then run on the GPU. That's all we need. Now, temporarily, we also have to tell it where the rock thrust library is. And this will also work on a workstation GPU. It will replace down here. We can replace all the allocations basically by a HIP managed memory call. And so that will allow it to run on the workstation GPUs as well. Even though we don't have managed memory on the workstation GPUs. So what are these? Okay, any minute now. Network must be slow. Okay, who's loading down the network? Okay, so here's an example, the serial code for transform. We add just this policy at the start. It will run on the CPU with that using TBB library. To get it to run on the GPU, we add the par unsequence command. Okay. So you have to write all your loops in some sort of form like the transform. Or there's a for each one also. But this is a little bit more change to your code than what we showed in Cocos. But it also is more C++ friendly. So it just depends on what kind of style you want. So this works really well for like a one-dimensional array where you're going to loop over. It's going backwards. So when you have data parallelism, you just want to split up across the processors, across the GPU compute units. It's a little harder with something like a 2D computation, especially if you don't want to compute all the elements. For example, if you've got a halo or a ghost boundary around the exterior, it's harder because we have to give it the information of what to skip. So we're going to use the standard for each, standard transform, standard reduce, to do each of these operations. And then supply this, this policy at the start. Now, here we got a for each, but we've got a reduction operation in here, so that's going to cause a problem. We have to use the reduction algorithm for that one. I think we've basically said that. There are some restrictions. I'm not going to spend a lot of time on them, but you can find that you are doing something which is not supported. You can't do exceptions, which makes sense. You have to have basically a random access iterator, which means we can operate on the elements of the array in any order. You cannot do dynamic memory allocation in the routine, which makes a lot of sense because you usually don't want to do that on the GPU. And then for interposition mode, which is a complicated way of saying we are going to allow this to run on the workstation GPUs and replace the memory applications. And there's some additional restrictions for that case. So what are the algorithms that we have in C++? Well, here's a list of them. There's a lot of them. I wouldn't even know how to use half of them. And I doubt most people would, but there are a lot of algorithms that are available in the C++ library. Most of these are supported by rock thrust. Not all of them, but most of them are supported in one form or another. So there's a couple examples of using HIP standard parallelism. You can try those examples and see how they speed up your code. Most of these examples are kind of small, so you're not going to get huge speed up. Here's a example of a for each algorithm. In this case, it looks quite simple. This is just a simple multiply an array by 5. A make file, so here's an example of the make file that you would have for this. So we have to include the HIP standard R in the compile, and then they are trying to make it automatic to find where the hipstand par path is. I think we include that in our module for the compiler, AMD Clang compiler. And then here's a transform example. So this is similar to the for each. Some people say this is the preferred form to use. And then here's the transform reduce call. So those are probably the more common ones you're going to use. This is an example of a typical computer science problem, the traveling salesman problem. So you can get this one. There's examples of the C++ standard parallelism that you can download, which implement it for this. So the only difference we have to do compared to the standard one you can download is we have to change the execution par to execution par unsequence. Because we don't implement the par version. And if we put that in the code, we can make this run on the MI300A. And this is more of a brute force approach. So it will check all the routes and come up with the solution. Another problem that we have done is something called the minimax problem. So this is a space filling problem where we want to place another point in space to the nearest placed point. So it's a greedy algorithm, and we want to basically place it for the optimal location in this space filling region. So the minimax for 4,000 elements, this is the timing for that problem by putting in the sequence, unsequence, and par and sequence policies. And so we take a code that took a minute to run and reduces it to 22 seconds. Very small problem, so we see a modest improvement in time. If we increase the number of elements, it's too long to even measure. And for sequence, we got 4 minutes down to 1 minute. And if we do 40,000, took too long to measure, and we got it down to a reasonable amount of 4 minutes and 48 seconds. With affinity, giving you better placement of the data, we can get it down to 4 minutes. So you can see it improves things, but a key here is that when we did this, we had to reduce the number of cores that we were using because there wasn't enough work to keep all 192 threads busy. So it actually sped it up to give it less threads. So it's an interesting technique to speed up some problems. It's not appropriate for everything, and it's still pretty early in the development phase. So it does leverage the MI300A because it uses the memory management on the MI300A for managed memory. So that makes it much more effective on the MI 300A. Okay, I think that may be it. So the questions or comments about what you think about this different approaches for C++ code. Your kinds of applications, which is more attractive, the standard algorithm or the COCOS, which I think is more like the idea of a for each loop to do the parallelism.
Some people like Julia.
Hmm?
Some people like Julia.
Well, I support Julia too. We have a lot of active people doing Julia. And we do have that running on the system, but there are some Julia tests we run. So I'd have to dig out the examples for that one if you're interested.
I'm wondering about kind of longer term development. If you're working on code, say for 5 years, keeps changing, 5-10 years. The risk of, I don't know what the risk would be of using COCOS or Raja when the development stops on that. Whereas maybe using something that's being slowly but surely integrated into a standard, you may just need to revise your code every couple of years to keep up with the standard.
So that's always a fear when we have a new language that comes out. And the biggest worry is that if it's a graduate student and they actually get a job, the language is gone. But COCOS is such a wide adoption at this point, it's not going to disappear. I think that fear is probably gone.
You say the same for Raja, or?
I think Raja too. All the Livermore codes are using it, and it's pretty widely spread. Now, whether they merge or, we have something that develops using the same concepts that absorbs those two, I don't know. But I think there's no danger that they're going to disappear. There's too much built on them now. The C++ is interesting, and it's more C++ friendly in that it's part of the standard, but it takes more change to your code to get it to work.
Yeah, those abstraction languages, they seem very inviting because they seem very simple to implement, like COCOS or Raja. But yeah, the one thing that sounds a bit worrying is the debugging. There's that one macro that expands into, I don't know.
Yeah, debugging COCOS code, it can be, if it's not working right, it can be difficult to figure out why, because there's a couple layers that the template expands, and it's hard to. If you bring it up in a debugger, what do you see? Because it's not your original source.
Yeah. Is that the templating problem or the macro that's in there?
It's the template.
It's a template.
Yeah.
But the number of templates, I mean, templating will increase or as more architectures come about.
Yeah. I'm afraid we got a lot of templating in code today.
Yeah.
And that is hard to debug, period. I mean, it's hard to debug a template because it gets generated. It may not even point back to where your original source code is. I actually think one of the more attractive standard-based languages is going to be Fortran with concurrent, because it's less change to the code than the other approaches. And we have a gap that is really serious in that there is no work being done on a C standard parallelism. And so there's this gap that, we've talked about since the 90s to have a for each or for all or something like that. And I don't see any movement to implement that. And that's a huge gap because you're going to want if you go standard parallelism, you're gonna have parts of your code in C that you need to get working. But it's interesting because I think this is showing you the trend that the compiler actually can do a lot of this. We really don't need programmers to be spending huge amount of time translating from one language to another. We had a summer project with a student that we worked on the L Fortran compiler, and we could take a Fortran loop, convert it to Cocos in C++, OpenMP in C++, and take that Fortran code, emit out C++ code in either of those languages, or even lower it in LLVM to compile it. Compilers can do all of this. It's just a matter of time before we get that technology there. It takes a long time for compilers to get developed. So 10 years from now, it may be that you just say, I have this GPU, just generate code for it. Maybe longer than 10 years. Compilers move slower. But there's no reason a compiler can generate for different CPUs. Why can't it? Why is a GPU any different? It's just a matter of time and effort. Anyway, I hope that gave you an idea where the industry's going. It is getting easier. The tooling's getting better. We'll be talking about debuggers and profilers, which are making things a lot easier. On day 3. So with that, I think we wrap up for today. So we're a little early. Use the rest of your time to explore the examples, or take them for homework and try some of them later. Any questions, you can ask them in the morning, and after you've had some time to think about these different approaches. So we've surveyed languages. Tomorrow we're going to talk about more advanced topics of programming, both OpenMP and HIP. Okay.